All right, everyone. So for this next section, we're going to talk about 5.3, the second derivative test. So in the previous section, we already talked about the first derivative test, and now I kind of want us to start off by knowing like what the difference between the two is and what we're using each one for. So whenever we're doing the first derivative test, that's going to help us determine what the critical points are. It's also going to help us determine where the function is increasing or decreasing. And of course, the last thing, which, we did all of this in the previous section, it helped us determine where the relative minimum and maximum are located, or local minimum or maximum, depends on which phrasing you want to use. All right, so that's what the first derivative is going to help us determine. What the second derivative test is going to help us determine is something called inflection points, which I'm going to go over a little bit more detail as we go on, but it helps us determine the inflection points. It also helps us determine whether where a function is concave up or concave down. And the nice thing about the second derivative test, and personally I would prefer this method for determining what the relative minimum and maximum values are. Okay, you can use both of them, but I think this method is a lot faster, especially if the second derivative is kind of a simple like power rule that you can do. All right, so now as far as concavity is concerned, very similar to what we did with the first derivative test, if we wanted to know where the function is increasing or decreasing, for the second derivative test, we're going to use that to determine whether something is concave up or concave down. So for concavity, what we're going to do is we're going to get the second derivative and then set it equal to 0. All right, and then, like kind of similar over here to find, when we set the first derivative equal to 0 to find our critical points, to find the inflection points, those are our x values, right? So before, our x values used to tell us what the critical points are, right? But for the second derivative test, that helps us determine what the inflection points are. And those inflection points are what's going to tell us whether it's switching from being a function that's concave up versus a function that's being concave down. So that's for the inflection points. Now, back then with the first derivative test, I'm kind of giving you the comparison here, but with the first derivative test, if the first derivative was greater than 0, we knew that those were positive slopes, and that means it was increasing. It's a little bit different for the second derivative test. If the second derivative of x is greater than 0, then that tells us that it's concave up. Whereas if the second derivative of x is less than 0, that's telling us that the function is concave down. All right? So let's kind of look at this function just to kind of help us, give us a better understanding of what's going on here. So obviously, you can kind of tell this function, right? If I look at this function, it does look like that it's concave up within this region right here. But if you kind of notice, like at this point right here, it kind of switches gears. Now it goes from being concave up, like it's concave up there, and then in this region, it kind of starts becoming concave down. Like you could just sort of see the curve is just sort of like, facing downward and opening downward. But then over here, it's kind of switches gears again. Like it starts like, changing direction, and now it's back to being concave up. But then over here, again, this is the inflection point there, and we look at this graph, and if we observe it, this region is kind of indicating that it's becoming concave down. So right here we have 3 different points of inflection, and that's the part that a lot of people struggle with. Is they say, the point of inflection is kind of like that point right in between that transition from being concave up to being concave down, right? So if we look here, there are 3 places where that's located. So our inflection points are x equals 3, 4, and 5, and that's where it changes concavity. Ignore that. So again, what you'll notice, like so basically if my inflection points are 3, 4, and 5, you have 4 different intervals or 4 different regions that we're working with. So you can tell that from negative infinity to positive 3, my second derivative is going to be positive because it's concave up, which means that, it's concave up. So in other words, if I were to plug in a test value here from negative, like it's, for example, let's say I plugged in a test value of 0. If I plugged in 0, then that's going to tell me that the rate of change of the rate of change, so the second derivative, is going to be a positive value, which is telling me it's concave up. If I plugged in a test value of like 3.5 here, and I plug that into my derivative, I don't really have a function to show you, but you'll see in the example up ahead. If I plugged in 3.5, then what that's going to do is that's going to give me a negative value, because you'll notice that in there it's concave down. And then from 4 to 5, it's concave up, so it's positive. From 5 to infinity, it's concave down, so that's negative. And yeah, that's pretty much going to tell us where, or like what's going on with the concavity from within each interval. All right. So let's actually apply this to a problem and see how it is that you're going to go about solving these problems. So whenever you're doing curve sketching, it is important that if you're going to sketch a curve, you should know where the relative minimum and maximums are. So we're going to go ahead and do that with the first derivative. So first we're going to find the first derivative. So that's going to become 4x cubed minus 4x. And then, of course, to find the critical points, we're going to set this equal to 0. So we have 4x times x squared minus 1, which is pretty much the same thing as 4x times difference of squares is x plus 1, x minus 1. So our critical points are located at 0, -1, and +1. I don't know why I put a parentheses there. So these right here represent our critical points. Now, well, let me go ahead and just do the second derivative while I'm in that mindset of doing power rule. So I'm going to do power rule again, and I'm going to end up with 12x minus 4. And then if I set my second derivative equal to 0, I'm going to have 0 is equal to 12x minus 4. I add 4, then divided by 12. Oh, wait, no. Sorry, this is supposed to be 12x squared. Sorry. So I add 4, and then when I divide it by 12, I'll have 1/3 is equal to x squared. So then my x values are going to be 1 over the square root of 3. And for those of you who want to rationalize it, well, plus or minus, sorry. And for those of you who want to rationalize, you can go ahead and say radical 3 over radical 3, or radical 3 over 3 if you multiply the top and the bottom by radical 3. So these right here, I'm just going to use this one because we should be rationalizing, but these right here are our inflection points, okay? So we have our critical points, we have our inflection points. Now, the one thing I want to show you guys is that you can use the second derivative to determine whether or not these critical points are maximums or minimums. And I'll show you right here. So like if I took the second derivative of each of these critical points and I plug those into there, well, let's see what happens. If I plug in 0, right, into my second derivative, I'll have 0 minus 4, which is -4. So when I plug in 0, if I have a negative value, kind of like what I was saying up here, when you have a negative value into your second derivative, that's telling you that at 0, the function is concave down. So if the function is concave down, well, I mean, and that's the critical point of that function, doesn't that kind of indicate that you have a relative maximum there? So that's what you do. So you can plug in your critical points straight into your second derivative, and if it's negative, that tells you it's a relative maximum because that tells you it's concave down. So on the other hand, if I had f double prime of -1, well, if I plugged in -1 into this, that'll be 12 times +1 minus 4. That gives me +8. So if I have a positive value in my second derivative, that's telling me that it's concave up. And you can just kind of see right there that you would end up with a relative minimum value there. And then if I did the second derivative of 1, I would also get 8. So that pretty much tells me that I have a relative minimum there too. All right. Sorry, I had to stop recording for a second. But anyway, so we went ahead and what we did was we got our critical points and plugged it into our second derivative. And that was going to help us determine what the relative minimums and maximums are. So now what we have to do is I'm going to go ahead and use this table to kind of help me determine where it's concave up and where it's concave down. So obviously my intervals, if these are my inflection points, we're going to set up our intervals very similar to how we did with the critical points. So one interval is going to be from -infinity to radical 3 over 3. The next interval will be in between, negative radical 3 over 3, sorry. The next interval will be in between negative radical 3 over 3 and positive radical 3 over 3. And then, of course, the last interval is going to be from positive radical 3 over 3 all the way up into infinity. So again, it's just kind of building off of what we did from the previous section. Now we're going to do a test value, and then from our test value, we're going to determine if it's concave up or concave down. So the test value I use over here, if that's, well, square root of 3 is probably between like 1 and 2. So I'll probably just say, I'll just go ahead and say that use -1 here. Actually, I think I can use the same thing as my critical points. Yeah, a value between here is 0. A value between there is +1. So, and the nice thing is I already went ahead and plugged these into the second derivative. So with this with the first derivative, when I plugged in -1 into my second derivative, I got a positive. With 0, I plugged it in and I got a negative number. And with +1, I got a positive number again for my second derivative. So this is pretty much indicating that it's concave up. This one is concave down. And this is concave up. All right. So that should give you a deeper understanding of kind of what's going on with the concavity. And I don't know how relevant curve sketching is anymore, especially now that all of us have graphing calculators. But just in case they do ask it, I know in college they really emphasize this a lot. So let's just go ahead and do that. First of all, if they ever do ask you to sketch a curve, it's going to be really helpful to know what the x and y intercepts are. So I'm going to calculate that down here. So remember, for the y-intercept, you got to make sure you got to remember to set x equal to 0, right? So if I set x equal to 0, well, when I plug in 0 into this, it'll be 0, right? So then my y-intercept is simply just going to be 0 for x, and my resulting y value was 0. So there's 1 point we know for sure. And then for the x-intercept, I'm going to go ahead and set either y or f of x equal to 0. And so when I do that, let's see, I'm going to set f of x equal to 0. Then I have x squared minus 2x squared. And then 0 is equal to, x to the 4th. I can factor out an x squared out of both, and I have x squared minus 2. So then my x-intercepts are going to be at x equals 0. And over here, if I set this equal to 0, I add 2 square root. So x equals plus or minus the square root of 2, right? Square root of 2, what is that? 2 square root is 1.414. So plus or minus 1.414. I like to know the decimal because I know I'm gonna end up graphing this. So I know that my x-intercepts are located at, well, 0, and we also have -1 point, so probably somewhere right there, and then positive 1.414 somewhere right there. All right, so we at least know our x-intercepts, and we have that plotted. Now, we should know that at -1, right, we know that we're going to have a relative minimum. And I might as well just figure out what that point is of my relative minimum. So at -1, if I plug that into the function, that'll be +1 minus 2 times +1, which is just -1. So I'll plot that point. And same thing if I plug in +1 into this, it'll be 1 minus 2 again, which will just be -1 there. All right, so I can pretty much kind of already determine that, you know, if this is a relative minimum, I know that it's going to kind of curve like that. And I know that if 0 is a relative maximum, it's going to kind of come up and have like a little peak there. But the other thing too is like radical 3 over 3. If I did that, I'm going to use my old school calculator, radical 3 divided by 3. We know that at plus or minus 0.58 roughly. So at like plus, so like 0.58 and here 0.58, we know that that's going to be where it kind of changes from being concave up to concave down. But I mean, I'm just going to curve the sketch like right here, just kind of like that. So I know it's going to look something like that. And I know that this is a relative min, and it's just going to go up from there. And that's going to go up from there. And you can kind of see it right there. Like really at 0.57, like that right there is the point of inflection. -5.7, that's another point of inflection. You can tell that like really before this point of inflection, it becomes concave up. In between these two, it's concave down. And in, you know, after this point of inflection, it's concave up, as kind of indicated by our intervals that we have right here. So it's kind of neat. We go, you know, we don't really know what the function looks like, but based off of all of this information that we, you know, calculated for and found, we can pretty much create a rough sketch of the curve. Is it going to look exactly like this? Probably not. But I bet you if you put this in your graphing calculator, it might look something close to that. All right. So the next thing that you're gonna see in your like in the notes is about particle motion. Like I said it in section 4.2. Particle motion is always something that the AP exam is going to ask. Every AP exam that I've looked at has several questions in the FRQ about particle motion, and sometimes they incorporate like a second derivative test with that. So let's kind of see what we have to learn over here. A particle is moving along the x-axis with position function x of t is equal to 1/3 t cubed minus 4t squared plus 12t. Find the velocity and acceleration and then describe the motion of the particle. So what you have to remember here is that if the velocity and the acceleration, if they have the same sign, it's speeding up. All right? Hopefully you remembered that. And if they have different signs, if v of t and a of t have different signs, then they're slowing down. That's essentially what we're trying to figure out here. All right, so let's go. First of all, in order to find the velocity and acceleration, we got to get our position function and find the first and second derivative. So I know that the first derivative, hopefully you remember that the first derivative of position is the velocity function. And when I take the first derivative of this, I'm going to do power rule. So I bring the 3 down to the front. That becomes just t squared. This is minus 8t. And then this becomes plus 12. All right. So that's our velocity. And then for our acceleration, we're going to do the second derivative of t. Right. So remember, second derivative is the acceleration function. And so I'm going to do the second derivative. So that's just going to be 2t minus 8. All right. So whenever we're trying to figure out whether something is speeding up or slowing down, we have to look at we have to figure out both the critical points and the inflection points and create intervals for all of those values and kind of see what's happening. So I'll kind of show you right here. And it'll be, this is the type of problem that would be easier explained through a table. So as opposed to that number line that I like to do for increasing, decreasing functions. So that's what I'm going to do. So first of all, I'm going to set this equal to 0. And this is factorable, so we just have a t squared in the front, so it'll just be parentheses t and t. Two numbers that multiply to give us positive 12 but add up to negative 8 are negative 6 and negative 2. Yeah. So then when we set each of these equal to 0, t is equal to 6 and t is equal to 2. So this right here, that's our critical points. And then over here, we're going to set this equal to 0, so we have 2t minus 8. If you don't know your algebra by now, I'm sorry, but it's going to be t is equal to 4. So essentially we have, we're going to be looking at the intervals between all of these values, between our inflection points and our critical points, because, those are from there we can determine whether something is increasing or decreasing or moving left or moving right. It'll just be better explained through a table. So obviously this is how I'm going to set it up. I have x prime of t in one row, which we know is the velocity. And I'm going to have another row with my x double prime of t, which we should know is the acceleration. I'm going to have a nice little table like that. And let's see, I'm going to have an interval from, well, we don't have negative time, so I'll do from 0 to 2. So from 0 to 2, that'll be one interval. Whatever. That'll be one interval. I'll do another interval from 2 to 4. I'll do another interval from 4 to 6. And then a last interval from 6 and beyond. Okay? So now I'm going to look in between these intervals, right, and see kind of what's the behavior of the velocity and what's the behavior of the acceleration. So obviously I can pick test points, and I have nice test points here. I could just pick 1 here, 3 there, 5 there, and 7 there. I'm going to use those as my test points. Right? So, and then I'm going to use those test points and plug it into my velocity function and my acceleration function. So if I plug in 1, well, let's see. If I plug in 1, I'm going to end up with 1 minus 6 times 1 minus 2. Those are two negatives, so I'm going to end up with a positive right there. Right? Actually, I'm just going to go ahead and work it out here. So I have f prime of 1. That'll be positive 5. If I do f double prime of 1, if I plug in 1 into this, that would be negative 6. If I plug in f prime, I'll use the test point of 3. into this, 3 minus 6 times 3 minus 2, that'll be negative 3. If I do f double prime of 3, I'll have over here negative 2. If I have f prime of 5, let's see, if I plug in 5 into that, negative 1 times, that'll be negative 3. And then if I plug in f double prime of 5, I'll end up with a positive 2. And if I do f prime of 7, if I plug that in that, I'll get 5. And f double prime of 7, plug that in there, 14 minus 8 is 6. All right, so just do the quick calculation here. And so you'll notice that if I do f prime of 1, so the first derivative came out to be positive. And hopefully you guys remember from 4.2 that if your velocity is positive, that means that you're moving to the right. Okay? And then my acceleration, well, that happened to be negative, right? So obviously that means concave down. But again, you have to remember, if you have different signs for your velocity and acceleration, then that's telling you that it's slowing down. All right? So I'll let you guys go ahead and decide from there what these other intervals are. If you want to know what the other answers are, then you can just go ahead and look at the filled in notes PDF that I'm going to post into Canvas. And I'll just leave it at that, and that's about it. So, well, no. I'm going to go ahead and do these next problems, but I'm going to pause the video and come back. So see you guys in a second. All right, so for these types of problems, it's pretty much similar to like what we saw before, where they give you the graph of the first derivative, and from this you can pretty much determine what the qualities are of the second derivative. So remember, if the second derivative is equal to 0, right? That tells us what our inflection points are. Now, I know I didn't really give you guys any directions in your notes, and I probably should have. But what I would have wanted you to ask is determine what the, let me put it up here. Determine the inflection points and intervals of concavity. All right. So again, what you have to remember is that the second derivative, when the second derivative is 0, then that pretty much tells you where you have your inflection points, right? So, and again, these types of graphs get really confusing because then you have to go back and forth from like your original function to your derivative to then now. Sometimes they'll even give you the second derivative graph, and just kind of going back and forth between the two make it really difficult. But you have to remember that if this function represents, or if this graph represents the first derivative, then the second derivative of the function is pretty much the slopes of the tangent lines of the first derivative, right? So take a second to think about that. If you had, because like before, if we had the original function, which I'm trying to find the previous page, but I can't. Oh, here we go. Like if we're looking at, if this was the original function, then the slopes represent the first derivatives, right? But here, if this is already the derivative function, then the slopes represent the second derivative, right? So just kind of think about that for a second. Hopefully, you know, obviously you can send me a message and maybe I can explain it more during Zoom, but I'll just kind of leave it at that, like that for the video. So if this represents the first derivative function, then we want to know when the slope is equal to 0, and that's going to tell us when the second derivative is 0, and that's going to tell us where what the inflection points are. So over here, if I kind of look at this, I know I have a horizontal tangent here, a horizontal tangent there, and another horizontal tangent there. So those right there are potential inflection points. So I have x equals -2, x equals +2, and x equals 0, right? So what we're going to do in order, and this is another important part that I probably should have emphasized earlier, but if you want to know whether or not this is an inflection point, you have to be able to, it's only an inflection point. Let me go ahead and bring back the other page. It's only considered an inflection point if the graph changes from being concave up to concave down, or from concave down to concave up. In this case, it's concave up. So the inflection here was So it's concave up, and then after that it becomes concave down. So this right here is an inflection point. But you're going to see in one of these cases that that's not really going to happen. But let's just kind of pay attention. So first of all, if we know that we're going from positive slopes to negative slopes, right, then that's telling us that from this region to this region, it's concave up. But from this region to this region, it's concave down. So we're going to go ahead and say that yes, x equals -2 is a point of inflection because it's going from, I'm sorry. It's the other way around. These slopes are negative. I don't know why I said positive, but it's getting sloppy. But anyways, so yeah, so if we're going from negative slopes to positive slopes, it means it's going from concave down to concave up. So from negative to positive, right? It changes signs. So therefore, x equals -2 is an inflection point. All right. At x equals 0, what you'll notice is that these slopes are all positive, but then after this point right here, the slopes continue to be positive. So right here, we know it's concave up. So essentially, this is not going to be an inflection point because if it went from concave up to concave up, that kind of defeats the, what the definition of what an inflection point is. So if it went from positive to positive, the signs are the same. So therefore, x equals 0 is not an inflection point. All right. But in this case, we have positive slopes on the left side of this and negative slopes on the right side of this. So if it changed from positive to negative, then this changes sign. Therefore, x equals 2 is an inflection point. All right. So now, if we want to know from what intervals it's concave up and concave down, well, we know from negative, as we established here, from negative infinity to -2. So from negative infinity to -2, we know that it's concave down. Oh, I should have also said and from 2 to infinity, we know that that's concave down. And we also know from -2 all the way up until +2, it's pretty much concave up the whole time. So from -2 to +2, we know it's concave up. All right. Oh, sorry. Didn't even realize that. But yeah, so essentially, yeah, we're from the first derivative graph, you can pretty much determine a lot of the different qualities about concavity as well. I'll go ahead and leave this one for you guys to do on your own. If you want to see how this, at least the solution for this one, you can go ahead and look at the filled in notes PDF on Canvas. So I'll leave you guys to it. And if you have any questions, of course, you're always welcome to ask me. So I'll let you guys go. Take care.